Hi, I'm Minae, and I'll be presenting for Andy today. So when we learn from humans, there are many forms of feedback we can use, such as demonstrations, preferences, physical feedback, etc. We typically pick one form of feedback and use data generated in that form to learn from humans. However, today, I'm going to focus on how we can specifically learn reward functions. So we asked the question, can we combine different forms of feedback to learn reward functions better? So in our task, consider a task where the robot needs to move its arm toward a goal while avoiding the obstacle and keeping the arm low. One way we can learn reward functions is to use inverse reinforcement learning. In IRL, we collect demonstrations, and from those demonstrations, infer a reward function. So above, you see Andy giving a demonstration via teleoperation. However, even Andy, who has a lot of experience in this task, struggles to provide a good demonstration. And this is not an isolated issue. When we invited people into our lab to similarly give demonstrations, many of them commented on how difficult it was to do so. So to put simply, it's hard to provide good demonstrations on robots and especially end effectors with high degrees of freedom. So if we can't use IRL, what can we use? Preference-based learning is another option. Here, we show a human two trajectories and ask her to pick which of the two she prefers. So for instance, a human may say, okay, since the robot's arm is moving closer to the goal in option 1, I'm going to pick that one. Notice how her preference encodes some information about the reward function. Therefore, by repeatedly querying the human, we are able to learn the true reward function. However, note that her response effectively only encodes one bit of information, whether she wants option 1 or option 2. So in practice, preference-based learning is actually really slow and takes many, many queries to learn the true reward function. Our key insight is that demonstrations are rich in information, but are relatively inaccurate. On the contrary, preferences are really accurate, but each individual preference query is relatively uninformative. Note how their strengths and weaknesses are complementary. So we ask the question whether we can combine information from both in such a way that amplifies their strengths and demolishes their weaknesses. And we think we can. Here's our idea. First, we collect demonstrations from humans, and then from those demonstrations, learn a distribution about reward functions, a prior, if you will. Now, although our prior may be imperfect, note that this prior effectively shrinks the space of possible reward functions. We can then use preference-based learning to learn a reward function in this much smaller space by repeatedly generating queries, getting feedback from humans, and then updating our distribution. And we repeat this until we converge on the true reward function. Also, since we're using preference-based learning in a much smaller space, there are far less queries required to learn the reward function. To validate our hypothesis, we ran simulations on the driving and manipulation domain. And as we expected, warm starting preference-based learning with demonstrations significantly reduced the number of queries needed to learn the true reward function. To see if this worked in practice, we ran a user study where users trained the robot using both IRL and our method DemPref. The robot then optimized over reward functions it learned, and this is what we found. Notice that the DemPref robot is successful at the task, whereas the IRL robot isn't. And this is because the IRL robot overfits to demonstrations from the user that worries about collision avoidance with the obstacle. We also asked users which system they prefer, and they overwhelmingly chose DemPref. So in conclusion, we showed how we can leverage different forms of feedback in order to better learn reward functions. Thank you.